So I work with Professor Ashok Kumar Pandey from IIT Hyderabad. So today my topic of discussion is just most of the topics that I want to cover already ma'am has covered. So that made my life so easier. So I quickly go through it and I try to finish those. Like I am going to present two talks. In a stipulated time, I try to present it in short manner. Okay. And the first topic of discussion is the design of open and closed loop architecture for the hexagonal beam-based MEMS accelerometer. This is the first time we are proposing a different kind of suspension beams which are not conventional. Usually, most of the conventional structures uses the uniform beam-based or curved beam-based. For the first time, we are introducing these hexagonal beam-based structures. So these are the table of contents for this discussion. Initially, I introduced to the introduction to the MEMS, and then I quickly go through the motivation and how the idea of hexagon has come into our mind, and then numerical modeling of these MEMS accelerometer using the MEMS plus lumped model parameter model structure, and then open and closed loop modeling, and then I will show the certain results based on the conventional excitations we daily on day-to-day basis we can see them. So many of you already know what is the microelectromechanical systems. Ma'am has covered in detail of that one. So quickly I will go through it, what it all about talks about. It's a combination of the both mechanical and electrical components together so that we can bring out the physical quantity into a measurable quantity so that we can sense what is happening into a particular mechanical phenomena that can be sensed by these sensors. These are the microelectromechanical systems. So where we have a combination of mechanical components, we integrated with the readout circuits where we take out the physical signal in the form of the voltages or capacitance, and we both combine together to form a sensor and bring to a particular measurable quantity that can be a capacitance or that can be a voltage or anything. So essentially, these are all together as a MEMS, and there will be different kinds of MEMS which are already available in the market. These are the different mechanical, electrical based, optical, fluidic, magnetic, and thermal. And fluidic, we can extensively see in the microfluidic channels, and the optical based measurements. We use the optical sensors like micrometers, and the electrical based sensors and RF circuits on all these things RF based structures are coming into picture, and mechanical where I have deal with most of my study in my PhD. So remaining there you can see the thermal and magnetic also. So these are the basic applications. Before going to further, I would just like to ask you one question. How many of you are carrying the accelerometer with you now? So each one of you, right? So we are daily surrounded by certain kind of sensors. Mostly we can say that as the IMU sensors. It's an integral part of our life. So most of my study comes from that. So in this our presentation, we mostly deals with the accelerometers, how they can be fabricated, how they can be modeled, and how we can do the further characterization, especially in terms of the electrical characterization. So this is the typical basic representation of the MEMS accelerometer, which measures the change in the acceleration or change in the velocity in a three-axis direction. And then we can see the gyroscopes. And best example I can say in the gyroscopes is your mobile itself. When you are seeing a particular portrait or landscape shot, right? We click on the rotate option. That works on the principle of the gyroscope and magnetometers. And then typically this is the MEMS accelerometer. This is the graphical representation of how it looks like the MEMS accelerometer. It works on the principle of the Newton's second law. Whenever you supply a certain external input to the system, it tend to change its equilibrium position from certain position to another. So correspondingly, change in the displacement happens. That displacement will be measured in terms of the electrical signals by using the interdigitated electrodes called combs. So this is the basic principle of the MEMS accelerometer, and it's a simple like I can say 2 degrees of freedom spring mass damper system that can be characterized by the mx double dot my double dot plus cy and ky is equal to ma external excitation that you are giving. Here the three important characteristics that one has to be keep it in mind as a mechanical engineer is the mass, damping, and stiffness. These are the three important parameters we keep on playing so that the improvement in the sensitivity can be seen. At the same time, how we can play with the damping so that the structure is so responsive to the external stimulations. So there are the various kinds of MEMS accelerometer. Among them, I mainly focus on the capacitive-based MEMS accelerometer, where they like the basic advantage comes from is in terms of linearity and the bias drift, as well as the is easy to fabricate as compared to other, and the best advantage in terms of cost also. So these are the inertial grade available MEMS accelerometer which are readily available in the market for a different for different applications. And the question is like, why you are focusing on the MEMS accelerometer? Is it the only money driven, or is any new technology involved in it? If the technology is already well saturated, then why you are going ahead? So that is the basic question which also comes in my mind when I was doing it. The only is the money is driving the market. No, it's not only the money. how the technology is how the technology is evolving day by day, and how we can incorporate different things into the new technology so that we can bring the better devices into the market so that that can be adaptable to the current scenarios. So these are the some statistical statistics in terms of economics. They are not only giving the importance why the accelerometer plays a crucial role in the market, because the nowadays the demand for the mobile is gone to the next level. Means every mobile is carrying accelerometer. That means the each electronic device containing the accelerometers. So that's the reason. One factor is the money, other is the technology. So that's where the money is not only the criteria, there is a motivation that should come from the technology that was given by the word. There is a plenty of room at the bottom was given by the Richard Freeman. With that motivation, we carry forward our work. So if you see conventionally, there are so many accelerometers which are readily available in the market. They are basically onto the simple configurations. I would say either uniform beam based or curved beam based or a kind of compliant mechanism based. So then we thought of like, why can't we test these structures with a different unconventional suspension spring? Then we come up with the idea of hexagonal spring. Where I have published one of these papers into the sensors and actuators, where we have given the basic idea of using the hexagonal beams into the pressure sensing applications, where we can see the better sensitivity than the conventional uniform beams. So that we pop up like, why can't we integrate these two different streams together so that we can see whether the variations are really relevant to our new technology, or if not, then what things can be done to improve the sensitivity of these devices. With that thought, we initially progressed. So these were some of the prefabricated structures which I have done in our lab. And these were the conventional MEMS accelerometer, where you can see here, they are using the geometric anti-spring phenomena where the curve beams are coming into picture. So this is the idea which we come up with. So basically you can see here in the black color is the conventional rectangular beams which are uniform in nature. Then many of the questions people, even the reviewer has asked me is, if it's easy to fabricate, then why you are going for the hexagonal? From our understanding, it is came to the observation that these hexagonal shapes provide the better flexibility and better damping characteristics over the conventional beams. So because that's what I mentioned in the initial my slide is like mass, damping, and stiffness. These are the three important parameters to characterize the any sensor in terms of mechanical characterization. So this by basically like what we did, like by taking the simple rectangular structures, by doing the some kinematic interpolation or kinematic manipulations onto those structures, we could able to achieve the hexagonal structure. That's with that idea, we fabricated different structures which are already there in my paper. Interested readers can go through it. So out of which we specifically focused on the hexagonal and we implemented them into the MEMS accelerometer. So these are some of the prefabricated structures using the what Priyanka has clearly mentioned, like based on the silicon wet bulk micromachining technology and isotropic etching. We fabricate these structures by increasing the number of units from 1 to 5. And there you can see here, this is the many people initially we thought this is the disadvantage of these fabricated structures. But later it turns out that these structures are providing the better flexibility. So when we tune these parameters, like in terms of dimensions, thickness, width, and length, where we can really see the advantage of these MEMS hexagonal beams into the real-time applications. So this is the one insight we found from our experimentations. And this is the paper. Interested reader can go through it. And then dealing with this MEMS accelerometer is always a cost expensive task. So we thought of, instead of doing it fabrication first, we began with the numerical simulations first. So as ma'am has clearly shown in our presentations that like they have utilized the Covent-Aware and MEMS Plus tool, the similar tools we have also utilized based on the FEM and lumped parameter model. Now I quickly give the glimpse of how the numerical modeling we developed in the MEMS Plus software. So where initially we'll choose a certain material database based on the silicon on insulator technology. So where the base substrate has the thickness around 400 micrometers and the structure we consider it as 30 micrometers. It is well versed with the MEMSCAP foundry technology. And then we need to define the process. What kind of process we are utilizing? We are using it to fabricate those structures. So mainly deposition, patterning, and what is that called? Deleting of the sacrificial layer once you fabricate them. This is like virtual representation of the actual process, what is happening into the real-time world when you are going for the, either it is a 3-layer process or 7-layer process. In hand, we are doing it in the numerically and then see how the structures are coming out. So once that one we need to choose the components. What are the basic components of this MEMS accelerometer? Basically the proof mass and the suspended springs, as well as the comb fingers that we have that are readily available in the software, numerical software. With the certain degrees of freedom, we have to find what are the particular degrees of freedom where we have to focus so that we can connect them and get the required mechanical property of the structure. So, and then innovator, where we all assemble together these individual components. As I mentioned, it consists of a number of components like beams, combs, plates, box beam. We need to connect them using the innovator, where we are by using the node to node connection technology. Like we have two nodes, two components together by bringing together at one particular location, node location, and fix them at that location. So that is the innovator does. And then finally, we did the simulations using the DC and AC solver, and then visualizer, where we can see the acquired mode shapes and convert them into the MROM. Then I will clearly talk about what is this MROM talks about in the later stages. So quickly, I'm going, this is the modeling phenomena which we have followed for our work. Now, where it's a basic microfabrication process, begin with the simple SY wafer to the anisotropic etching. And there we can see the 3D fabricated structure virtually, not in real time. Okay. So those are some of the components of the fabricated structure virtually. Okay. So then we take the advantage of this numerical computation by bringing the MEMS Plus and MATLAB together. So what we did in the MEMS Plus, we created the entire microfabrication phenomena into the MEMS Plus, and then we integrated those structures into the MATLAB by using our own scripting. And then we can utilize the utilities of the Simulink, where we can build the individual blocks of the controls so that we can get the clear understanding of what the system is behaving for the different external excitation instead of doing it for the actual fabrication. So this is one of the mode shape. This is a working mode shape. It's an in-plane one, which is having the frequency of 875. It's a low frequency application. And then this is the architecture that we followed, a simple open and closed loop mechanism. Many of you already know the basic difference between the open and closed loop. In the open loop, we don't have any sensing feedback mechanism to control the system into the effective level. Where in the closed loop feedback system, we can feed back the signal to the system again and find the error. And if the system has to bring to the equilibrium by supplying an external excitation or control voltage, we will bring back the system to the equilibrium position. This is the basic difference between the open and closed loop. Yeah, I can. So these are some of the results which we found from the different external excitation. Begin with the step signal, and then we ramp signal, and we can see the clear advantage of using the closed loop MEMS architecture. And then this is the basic sinusoidal, which are most of our external excitation in the periodic in nature. So the better advantage, in the right side plot, you can see that the closed loop is providing the better sensitivity in terms of the sensing as compared to the open loop. So in the later talk, then how we can take the advantage of this closed loop into the another device that I can talk in the next lecture. So these are some of the conclusions which we can, qualitative conclusions I can say. These have been derived from our work. One is the better sensitivity and the better control over the initial transients in the system. So these are the certain differences which we followed for our preliminary work. And I would like to acknowledge my Professor Ashok Kumar Pandey, and one of my colleagues is a postdoc, Nikul, Jani. And we took the financial aid from the DRDO as a part of our project. So thank you everyone.